Well, good afternoon, everybody. Before we start today, again, please note that your homework from last time is up here at the front. There were very few problems with the way you solved the problems on this homework. Most students seemed to know what was going on just fine. You know, there was one problem where it talked about a number of tons of coal, I believe it was. You could have either assumed one short ton, which is 2,000 pounds, or 1 metric ton, which is actually 2,200 pounds, or 1,000 kilograms. And you would have gotten either 30% or 33%. But, you know, students really had very little trouble solving these problems. So I really have very little to comment on. You know, as usual, the solutions were posted outside my office. So you're welcome to go look at those. Also keep in mind that your second midterm is on Monday, so we will still meet in here, but we're not going to record it just like the last one. And I'll set aside about 10 minutes at the end today to talk more about the midterm. So with that in mind, let's just go back to where we were last time. And recall that we're in Chapter 7 now. We're talking about calculating entropy changes. Okay? We know that if we have a substance like water or the refrigerant 134A where we have property tables, then we just look up the value of the property entropy in those tables. It's very easy to do. We've got superheat tables, we've got saturation tables, the entropy data is there like all the other data. But we have to do it differently if we have solids or liquids or ideal gases because we don't always have good tables available to us. So just like when we were talking about the first law, we have to use specific heats in order to calculate entropy changes, just like we had to use specific heats to find internal energy changes or specific heats to find enthalpy changes if, again, we have ideal gases or solids and liquids. Now, last time I derived an equation for you specifically for either solids or liquids, and the basic equation was that the change in the specific entropy was the heat capacity, which, remember, is the same as specific heat at constant pressure or constant volume, and then multiplied by the natural log of the temperature ratio. Now, one of my assumptions within this is that C is a constant. I mean, we had our differential equation that basically said ds equals cv dt over t. I could have just integrated that whole thing if I had a value of the heat capacity that was a function of temperature. But we just don't have that for solids and liquids. We have values of heat capacity for various temperatures for various liquids and solids, but we don't have any sort of functional relationship between C and T, so there's no way we can integrate. So this equation that was derived last time assumes that we're using C as a constant. And our preference would be to use this at the average temperature. I mean, that would be preferred. But we don't always have data at a variety of temperatures. Remember that in Table A2 Part B, there's only 6 gases in there where it gives you specific heat or heat capacity. I'm sorry, A3, I was talking about ideal gases. In Table A3 for solids and liquids, there are very few substances listed that actually have the value of this heat capacity over a variety of temperatures. So for many, many problems, in fact, I'd even go so far as to say for most problems, you're just going to have to use the room temperature data that's presented in that table, again, Table A3. So we find C at the average temperature, that's preferred, or we can find it at the room temperature. You know, this is OK. But that's only if the T average data is not available. Okay. And this is the same thing that I mentioned, you know, several weeks ago when we were talking about this with regards to internal energies and enthalpies and the first law. So with this in mind, let's solve a problem now. And this will be number 7-60 from Chapter 8, and it's over here on the screen. I'm sorry, not Chapter 8, from Edition 8 of your textbook. So this is problem 760, again from the 8th edition. All right, so let me just read it as you're looking at it here on the board. It sounds pretty simple. In fact, it sounds practically the same as a problem that we did in class a month ago. So we have a 50 kilogram copper block that's at 140 degrees Celsius, and it's dropped into an insulated tank that contains 90 liters of water at 10 degrees Celsius. Determine the final equilibrium temperature and the total entropy change for this process. Okay. Now, let's just note that this is a quenching problem, right? When you're working metals and you want to give them the physical properties you need, you heat them up, liquefy them at a certain temperature, and then you cool them. You can cool them slowly, you can cool them abruptly, you can cool them in different fluids. But that's going to actually change the nature of the material. And if you've taken ME 218, 219, you kind of already know this, right? So we're not going to talk about that. We're just going to look at the problem. Now, it's a well-insulated tank, which tells me that there's no heat transfer, which will be important when we solve the first law. It says that we have a block of copper, and it's dropped into water. The diagram's a little bit small. Hopefully you can see it. It tells us some information. So it says that the mass of the copper is 50 kilograms. It tells us that the initial temperature, so T1 for the copper, is 140 degrees Celsius. By the way, Cu is a chemical symbol for copper, if you did not know that. Again, it's an insulated tank, so there's no heat transfer. And the tank contains 90 liters of water, so we know the initial volume of the water, and that's 90 liters, which is what, 0.09 cubic meters. And then we also know the initial temperature, so T1 for the water is 10 degrees Celsius. Okay. So let's make sure I didn't miss anything. Yeah, that's right. All right, so what we're trying to find then is the final equilibrium temperature. Now, equilibrium temperature means that the water and the copper come to the same temperature. So T2 for the copper and T2 for the water and T2 are all the same, and that's what we're trying to find. And we're trying to find the total entropy change for this particular process. We should keep in mind that because this is well insulated, there is not going to be any heat transfer into the surroundings. So the total entropy change is really just going to be the entropy change of the system. And again, we know this is because there's no heat transfer. And we would note further that the entropy change of the system then is going to be the entropy change of the copper plus that of the water. So this is what we ultimately are having to find. So again, this is unknown to us. Now, they specifically asked me for the final equilibrium temperature, but quite frankly, if they hadn't asked for that, we would have had to have found it anyway. If you look at the equation for the entropy change for a solid or a liquid above, we need both the initial and the final temperature. So we really have no choice but to solve the first law first in order to get the final thermodynamic state of the copper-water mix system, if you will. That will allow us to find the temperature. And then with that, we will move on. Knowing the temperatures, you should see it's pretty easy then to just look up the heat capacity in the tables and ultimately find the entropy change. So maybe I should then write this a little more and say that this is just going to be, and by the way, this is the specific entropy change. So we really need the total entropy change. So this is the mass times the heat capacity times the log of the temperature ratio for the copper, and then the mass, heat capacity, and natural log of the temperature ratio for the water. Make sure that gets on the screen. So this is what we really are trying to find. So again, it should be pretty obvious. We can find the mass pretty easily. I'll get into that in a minute. Well, we know the mass of the copper. We know the volume of the water. We can find its specific volume and thus its mass. We look up heat capacities. We know T1. All we don't know is T2. And again, that comes from the first law. So like the previous problems that we've seen, second law problems are really just first law problems. Well, they start as first law problems, and then we solve the second law problem beyond that. So what would be the appropriate first law? Keep in mind, these are closed systems. So heat transfer is going to equal the change in internal energy. Whoops, that's supposed to be a minus. And then plus the change in kinetic and potential energies, and then plus the work. I guess I'll put a little 1, 2 here. So we know we're going from some initial state 1 to final state 2. And let's note further that we're going to assume that both kinetic and potential energy changes are 0, just like we've done for every problem involving closed systems, right? So our first law then just simply becomes heat transfer equals change in internal energy plus work. Now, this isn't really quite complete yet, right? Because after all, we don't just have a single substance with a single internal energy change. We really have two substances. So if we think back to the problem that we looked at previously, I really have to separately find the mass and internal energy change for the copper and for the water. I mean, I did the same thing up here when I found the entropy change. I'm going to do the same thing here with regards to the internal energy change. So really, I want to write mass times U2 minus U1 for, well, I'll keep copper first, and then mass U2 minus U1 for water next, and then again plus the work. And then we might also recall that the first law for solids and liquids requires us to use heat capacity in order to find internal energy changes, right? It's just the heat capacity times change in temperature. So this really becomes MC T2 minus T1 for the copper plus MC T2 minus T1 for the water, and then plus the work. Now, I don't know why I've been carrying this work term through the whole time. I've already neglected kinetic and potential energy. In this particular problem, it doesn't tell us that there's any kind of a mixing device or anything like that. Often you would have some sort of a mixing device to, help the water circulate around the iron block and presumably give you increased heat transfer rates. But that's not the case here, right? There's no volume change because it's a sealed tank. So there's no boundary work, no mixing, no shaft work, nothing. So I honestly should have, up here at the top, just neglected the work. So that's going to be 0. Oh, what about the heat transfer? It's also 0, isn't it? It's well insulated. Q is equal to 0. So I really should have gotten rid of this term up there as well. So the equation we really have to solve for is that 0 equals MC times temperature change for the copper plus MC temperature change for the water. All right. Now, hopefully you can see that once we've solved the first law problem, we get the T2, then we just plug it in to the entropy change equation above, and we can find the entropy change. Yeah?
If we wanted to find the heat transfer between the materials, we would just set that equal to Q though, right?
Yeah, because ultimately the heat gained by the water is going to be equal to the heat lost by the copper. So you could certainly say that, M delta U for the copper is going to be equal and opposite to M delta U for the water. And again, without any heat transfer or work or kinetic potential energy, that would be perfectly acceptable. Yeah. All right, so how do we approach this? Well, actually, we know how to approach it. What we don't have yet is all of our data. So we need really a couple of things. First of all, we need the mass of the water. Yes. So the mass of the water is just found in the usual way, volume over specific volume. Now, presumably, although they didn't tell us specifically, but presumably this tank just sits there at atmospheric pressure. And at the given 10 degrees Celsius, that temperature is well below the 100 degrees saturation temperature for water. We know that water boils at 100 degrees Celsius, right? So clearly, this is going to be a compressed liquid. In other words, the specific volume is going to be about the same as that of the saturated liquid at the same temperature. So we can find this right away. We're given that the water volume is 90 liters, or 0.09 cubic meters. If we go into the appropriate table, which of course we know is our water table, so that's A4, we get that the specific volume is 0.001 cubic meters per kilogram. And therefore, we get 90 kilograms as the mass of water. We're also going to need some heat capacity data. So here we would go into table A3. And perhaps I should switch over to this table now, since we haven't done something like this in a while. OK, so here's my, oops, too far. All right, so we have 3 parts, right? Table A3, part A is liquids. So we should be able to find the water data down here at the bottom. By the way, before I proceed, I know that I've said many times that we don't really want to be using this heat capacity data for something like water or the refrigerant because we have really good property data in our tables. We don't have to use this C delta T method. We could just take the internal energy data directly out of our property tables and use it that way. This would be saturated liquid data at the appropriate temperatures. We can do that, but again, this particular problem is used to illustrate how one solves a typical solid or liquid problem. So I'm going to use the method of this section, which deals with the heat capacities. So back to table A3. You can see that it does give me water at 0, 25, 50, 75. I have a little bit of a problem, though. I know the initial temperature is 10 Celsius, but I really have no clue as to what the final temperature is going to be. I know it's going to be something less than 140 degrees Celsius. I just don't really know how much less it's going to be. So we're kind of stuck. I could just take the data at room temperature if I wanted to, and then hope that I'm going to be somewhere in that range. Although if we look at the numbers, we're going to be at about 4.19 or so at 10 degrees Celsius. And it's not going to change much. It's going to be 4.18 all the way up over 50, and then it's going to go back to about 4.19. I think I'm still going to be in that general range. So why don't I just assume that the average temperature, and again, I have to assume this because I just don't know it, is somewhere around 25 degrees Celsius. Again, I don't know for sure, but if I'm somewhere in that range, anywhere between 10 and 100, it's still going to be about the same number. And the heat capacity is 4.18 kilojoules per kilogram per Kelvin. OK, so whoops. There's our specific heat data. And then for copper, well, we kind of have the same problem, don't we? We know copper is going to start at about 140. It's going to end probably somewhere in the middle of the range. I don't know, 50, 20, somewhere in that range. Again, I just have to make some sort of an estimate. So I might as well use something that I think is going to be reasonable. I'm just going to use the data at 27 degrees Celsius. Okay, so granted, the average temperature for the water is going to be different than the average temperature for the copper. They both end at the same temperature, but the copper starts higher. So let's, again, just make an assumption here. I have to assume this, that it's about 27 degrees Celsius. And then again, I could just pull a number directly out of the table. And that's that 0.386 number. So 0.386 kilojoules per kilogram per degree Kelvin. Right. I might note, if we look at these heat capacity numbers, the heat capacity for water is more than 10 times greater than the heat capacity for copper. And believe it or not, heat capacity is a measure of how much energy that substance can hold. You can hold a whole lot more energy in a kilogram of water than you can in a kilogram of copper. So with that in mind, I would expect that the final temperature is going to be closer to the water's initial temperature than the copper's initial temperature, just because the heat capacity of water is so incredibly much higher. And we'll see that that is going to be the case, but we'll get to that shortly. So I'm actually done now with all the data. Let's just solve the first law. So we go back up to the first law equation, and we get 0 equals, so first is the copper data. So we're told that we have 50 kilograms of copper. Heat capacity, 0.386 kilojoules per kilogram per Kelvin. T2 minus T1 And the initial temperature of the copper is 140 degrees Celsius. By the way, I could convert this into Kelvin if I wanted to, but you may recall that when we have a temperature difference, it doesn't matter whether we use Celsius or Kelvin. A degree of Kelvin is the same as a degree of Celsius, and therefore any temperature difference in Kelvin is the same as that in Celsius. So I'm just going to leave these temperatures in Celsius, even though it really is a temperature difference in Kelvin. They're the same. And we did exactly the same thing on the other problem we looked at that involved only the first law here. All right, so there's my copper term, and then we add to it the water term. So we have 90 kilograms. We multiply that by 4.18 kilojoules per kilogram per Kelvin, and then T2 minus T1, and the temperature was 10 degrees Celsius initially. And we just simply solve for T2. We go through the math, and we actually end up with 16.4 degrees Celsius. So it turns out I really am a whole lot closer to the initial water temperature than the copper temperature. First of all, I've got almost twice as much water on a mass basis, and I've got 10 times greater heat capacity, so I would figure I'd be probably 20 times closer to the water initial temperature than the copper's. Anyway, if you look at this and now kind of compare this to the average temperature, well, the average temperature of the water is only going to be about 13 degrees, and if we go back to our water data, I'm still going to be pretty close, right? I use 4.18 at 13 degrees. We're actually going to be at, what, 4.20. What is that, 0.5% error? I mean, the fact is that we're assuming that these are essentially somewhat idealized processes. We're assuming a constant value of heat capacities. They really aren't. I mean, it might approximately be that, but to be off by a mere 0.5% is negligible. So I'm happy with the heat capacity that I chose for the water. And if I look at the heat capacity for the copper, well, again, my average temperature from 140 down to 16. So that's what, about 75 approximately. I probably should have used a number that was closer to maybe 0.390 instead of 0.386. But again, I'm off by what 1%? And that's just so small. I'm going to just say, you know, I don't want to redo the problem. My numbers are certainly going to be close enough. So I'm satisfied. Heat capacities are OK. Let's now find the entropy change. And it's
The average, that would be basically what we assume T2 is going to be?
no, T average would be the average of T1 and T2. Yeah, so, you know, because we're assuming that C is constant at the average temperature, and I'm just kind of checking to make sure my average temperature is pretty close to what I assumed, and that the heat capacity that I chose from the tables is pretty close to what it should have been. So again, I'm within 1%. I'm very happy with that. So now let's finish the problem and find the entropy change. So, you know, back to the equation from above. So delta S total is going to equal MC log temperature ratio for the copper plus MC, and then the natural log of the temperature ratio for the water. So just plug everything in. Well, we have 50 kilograms, 0.386 kilojoules per kilogram per Kelvin, and then the natural log T2 over T1. Now, this is a temperature ratio that we're actually using in the equations. Temperature ratios certainly do depend on whether we're talking about Kelvin or Celsius, right? So we absolutely have to use the absolute temperature scales. That's kind of a pun, isn't it? So T2 is 16.4 plus 273.15. T1 was given to us as 140 plus 273.15. And then we add to it the same for the water. So 90 kilograms times, 4.18 kilojoules per kilogram per Kelvin. And then the natural log of, well, the same T2, 16.4 plus 273.15. And then the initial temperature was 10, so 10 plus 273.15. Okay, so we definitely have to convert temperatures into kelvins. All right, so we go through a little bit of mathematics, and we end up with, see, minus 6.864 plus 8.388. So those are the two results for the copper and the water, respectively. And then we add them together. We get a positive value of 1.52 kilojoules per Kelvin. Yeah. So there, then, is an example problem. And the fact that we have a positive entropy change tells us that this process is certainly possible. Okay. So are there any questions on this particular example problem? Again, it's identical to the problem we did in Chapter 4, but we just add to it the entropy change at the end, and the first law problem becomes a second law problem. By the way, if I had asked, is this process possible, or is this process reversible, irreversible, or ideal, that would have been an acceptable way to state the problem. I didn't have to say, find the total entropy change. I could have simply said, is this process possible? And you would know it means exactly the same thing, right? So again, any questions? All right. So now let us talk about ideal gases. Okay. So to solve problems involving entropy change for ideal gases, we're actually going to start with a similar equation. I'm going to have to derive this, and it also is going to have to be derived from one of those TDS relationships that I gave you earlier. So what I want to do is start with this of the TDS relationships, whoops, the one that says TDS is equal to du plus p dv. So this is what I want to start with. Now, first, let me just divide by temperature. So I get ds equals du over t plus p over t dv. And then what I want to do is I want to remind you that an entropy change, an internal energy change is CV times the temperature change. And I also want to remind you that for an ideal gas, PV equals RT, or if you will, P over T equals R over V, right? And then plug these in above. So what do we get? We get ds equals, and here we have CV dt over t, and then plus, instead of p over t, we have r over v dv. Okay. Now, this is the differential form of the equation that I'm interested in. I'm interested in finding an entropy change, so let's integrate. Okay. I think the camera moved. Last week this was down here. Now it's up there. Okay. Let's integrate. Yes? Oh, yeah, that'd be fine. We're not going to need a computer for the time being. Okay. There we go. All right, so now I'm going to integrate. So the integral of ds, and let's just say it's from 1 to 2, is going to be S2 minus S1. And again, these are specific entropies, right? So this is going to be the integral of CV dt over t plus the integral of R dv over v. Now, I will note that R is a constant, so it's going to come out of the integral. So I could further rewrite this as the integral from 1 to 2 of CV dt over t, and then plus R. And then we should remember that the integral of dv over v is just the natural log. And applied between 0.1 and 0.2, it's the natural log of v2 over v1. So this is the equation that is applicable for these types of problems. But again, we have to think back to when we were talking about this material in response or in solution to the first law problems, I do have a table for ideal gases that gives me a relationship, a functional relationship between specific heat and temperature, right? It's from table A2 part C. But I've also said that I'm never going to ask you to actually do that. I don't want you to have to take the CP bar data from A2 part C and then convert that to CV data and then go through an integral of a third order polynomial equation. It's not that you couldn't do it, but it would be perfectly acceptable to me if we just estimate CV as if it were a constant. So if we assume CV is equal to a constant, and again, it would be preferred to take this at the average temperature, or, of course, if we don't have the average temperature, then we take it at room temperature. Remember, T0 stands for room temperature. Certainly, T average is best. Anyway, if we assume CV is a constant, then it comes out of the integral, and the integral dt over t is, well, it was the same as the integral dv over v, right? It's just a natural log evaluated between t1 and t2, so that's log t2 over t1. So we have CV log t2 over t1, and then plus r natural log v2 over v1. And this is how we're going to solve for our problems. This is how we're going to find the entropy change for an ideal gas. Yeah. So I will note that there is an alternate form of this equation, and there's different ways to derive it, but I'm just going to derive it very quickly. And I'm going to start with the other TDS relationship from earlier. So from TDS equals dH minus VdP. Remember, again, this was one of those relationships that I just gave you. It will be developed for you in your ME 302 course, but we need it now. So just like the author, it's just presented to you, and you have to accept on good faith that it's a valid equation, which it is. So we start with this equation, and we're going to do much the same as we did above. So ds, will be equal to dH over t minus v over t dp. We also want to note that an enthalpy change is Cp times the temperature change, right? So dH equals Cp dt. And then also, we want to remember that PV equals RT. And as such, V over T is going to equal R over P. They're very similar to what we had before. And we'll just plug those in. So we plug those in above, and we get ds equals, well, Cp dt over T, and then minus R over P dP. And just like before, I'm going to integrate. So the integral of ds is just S2 minus S1. So I get the integral of Cp dt over T, and then minus the integral of R over P dP. And then let's also keep in mind, again, just like the previous problem, that I'm just going to have you use Cp either at the average temperature or at the room temperature, right? It's just a constant value. So for Cp equals a constant, we basically would get now that S2 minus S1 equals Cp, which just leaves us with the integral of dt over t, which is again the natural log. So Cp natural log t2 over t1 minus, and then again, r comes out of the integral, and the integral dp over p is again the natural log. Evaluated from 1 to 2 is natural log p2 over p1. And this then gives us an alternate equation that we can use. So either of the two equations that I've underlined are appropriate to use in this class. You just have to look at the problem and what data is given to you. If you're given a problem where you know specific volume and temperature data, then you'd probably want to use this earlier equation, the one that includes the specific volume. If you're given a different problem where maybe you have pressure and temperature data, well, then you want to use this latter version of the equation, which includes pressure. You'll get exactly the same result, but you might as well use the equation that's going to be the easiest one to use for your particular problem. Now, one other thing that I want to note here, if we look at this integral of Cp dt over t, that actually is a special integral. Sometimes we call it an S function. Other people call it an isentropic compression function. Those of you who have been diligently reading the textbook have seen that when we have problems involving an ideal gas, specifically for air, we can actually go into table A17. And table A17 is an air table that gives you data for entropy and internal energy. But what it will also do is it'll give you data for this integral of Cp dt over t, this S function. We are not using that, though, right? We're not using table A17. I've mentioned that before, and I want to mention it again, that we are never going to be using tables like A17. Actually, it goes all the way up to about A25 for a variety of different gases. We're just not using that in this class. It's something we will learn how to use in ME302, but we're not going to use it here in ME301. So because of that, I just want you to ignore anything that talks about how to use these entropy functions, again, this integral of Cp dt over t. Ignore anything you read that deals with the use of table A17 for getting internal energy or enthalpy data. Now, that doesn't mean it's wrong if you use it. It just means that we're not covering it in this class. On your midterm, for instance, next week, if you use data from table A17 and you've used it correctly, you've learned it on your own and you've done it correctly, I'll still give you full credit for a problem like that. I'm not telling you I'm going to have a problem like that. I'm just saying that I'm OK with you using that information. It's just not something that is what you're responsible for in this class. All right, so we have the equations we need now. Let's do another example problem. Now, let me also remind everybody that the equations that I've developed here are applicable to both open and closed systems, right? The previous example problem we did, granted it was for a solid and a liquid, that was for a closed system, and 1 and 2 represented initial and final states within that closed system. But this would also apply to steady flow processes, specifically single stream steady flow processes. Those are the most common types of processes we're going to analyze. Those are the chapter 5 kind of problems. And as such, 1 and 2 will represent inlet and exit conditions. So you use the same set of equations to find entropy changes for first law, pardon me. You're going to use the same types of equations here. I'm sorry, I lost my train of thought. Maybe I'm a little upset today. Nonetheless, if you have an ideal gas, you use the same, well, I shouldn't even say ideal gas. If you have a closed system versus an open system, you'd use the same equations to find the entropy changes, which is a little bit different than the first law, right? For the first law, your closed systems would use internal energy change, and your open systems would use enthalpy change. So there's a slight difference there, but here, same equation. So let's do an example, and this is number 7-81. Again, from the 8th edition of your textbook. So it looks like I'm going to need the computer up on the screen again. All right. So let me read this to you. It says air enters a nozzle steadily at 280 kilopascals, 77 degrees C, with a velocity of 50 meters per second, and exits at 85 kilopascal with a velocity of 320 meters per second. The heat losses from the nozzle to the surrounding medium at 20 degrees Celsius are estimated to be 3.2 kilojoules per kilogram. Find the exit temperature of the nozzle and the total entropy change for this process. Okay. So here's my nozzle. We know that we have air, and we know that we're given inlet and exit conditions. We know P1 is 280 kilopascal, and T1 is 77 degrees Celsius. And V1 is 50 meters per second. 85 kilopascals is the exit pressure. And the exit velocity is much higher. I mean, that's what nozzles do, right? They accelerate fluids. So the velocity comes out quite a bit greater at 320 meters per second. Heat losses to the surroundings at 20 degrees are 3.2 kilojoules per kilogram. So we're actually given two things there, right? We're given the temperature of the surroundings of 20 degrees Celsius, and we're also given the heat transfer. Now, it's given on a per unit mass basis, so Q12 is 3.2 kilojoules per kilogram, and it's negative, right? It's heat being lost or rejected from the system, so we need to make sure we include the minus sign. So that's the data we're given, and we're told that we want the exit temperature, and we're told that we want the total entropy change for this particular process. Now, I do have to make one comment on this problem. I like the problem, but I do find that the author sometimes makes little errors. We have no information on the mass of the air that's moving through the system, do we? So how can I find a total? We need to know the mass. What the author really meant to say was find this total specific entropy change for this process. We just don't have enough to find the total because we don't have any mass information, nor do we have any information that allows me to find the mass. So I'm just going to note that for you and note that it's really the total change in specific entropy that the author had intended to say we're trying to find for this problem. Okay. Again, sometimes the author does that, and we just have to be aware of it. All right, so how do we do that? Well, we know that we're going to use an appropriate equation from above. It's not clear yet which one we use, but we'll figure that out shortly. And we also know that regardless of which of those two equations we use for the entropy change, we certainly have to find the exit temperature first, which means that this is a first law problem. Okay. And clearly it's a single stream steady flow problem. So what would our first law look like here? Now I'll write it on a per unit mass basis. So heat transfer minus work is going to equal the change in enthalpy. And let me put little 1, 2 subscripts here. And then plus the kinetic and potential energy changes. Now, we can neglect the potential energy change, but we certainly cannot neglect the kinetic energy change. I mean, we're given velocities, so if you're given velocities or enough information to find velocities, you certainly don't want to neglect the kinetic energy change. So I'll write that out. So enthalpy change plus, and this will be V2 squared minus V1 squared over 2. Now remember, this is specific. It's on a per unit mass basis, so there's no mass term in there. I might also note that it's a nozzle, it's a passive device, so there's clearly no work associated with this problem. So that goes to 0, and we end up with then heat transfer equals a change in enthalpy plus change in kinetic energy. Let's further note that we're talking about an ideal gas. The only method we have to solve these problems are ideal gas methods, right? It's not a real gas. Well, it might be a real gas, but we don't have any method which allows us to use real gas information, so it's an ideal gas. So we know that for an ideal gas, isn't the enthalpy change equal to the specific heat times the temperature change? All right, so that's the version of the first law that we are going to be solving for. Now, one other thing I guess I should note, which of the two entropy change equations would be the appropriate ones to use? Personally, I'd rather use the last one that was derived. After all, we're given both the inlet and the exit pressures, P1 and P2, so I may as well use the version, the version of the equation up here that uses those pressures. I mean, I could always use the ideal gas equation of state, and from that, find the inlet and exit specific volume, but I mean, why do the extra work? So I'm just going to use the entropy change, and that's the total entropy change I'm looking for. So I'll use S2 minus S1. for the system plus the surroundings. Keep in mind that for the surroundings, it's Q surroundings over T surroundings. So for the system, again, it's that ladder equation. So I just get Cp times the natural log T2 over T1, and then minus R natural log P2 over P1, and then plus Q surroundings over T surroundings. Please note that we have to include the delta S for the surroundings in this problem because there is heat transfer to the surroundings, right? In the previous example problem, it was a well-insulated vessel. There was no heat transfer. So it's not like we didn't calculate the entropy change of the surroundings. We just noted that it was 0 because there's no heat transfer into the surroundings. Here we have to calculate it specifically. So this is the equation that we need to solve second. Really, the only thing left for us to do is find the value of Cp and plug away into the equations. So we'll do that next. Now, again, I have a little bit of a problem, right? I know the inlet temperature is 77, but I have no idea what the exit temperature is going to be. I suspect that the exit temperature is going to be less than the inlet temperature. We're basically converting internal energy into kinetic energy. So we would expect that as we accelerate, the internal energy, or really I should say enthalpy, not internal energy, but we would suspect that the enthalpy is going to have to drop as the kinetic energy rises, and as such, we would expect that T2 is going to be less than T1. After all, enthalpy and internal energy are functions of temperature, right? As the temperature goes up, the enthalpy and internal energy go up. As the temperature drops, the enthalpy and internal energy go down. So we would expect that the enthalpy is going to drop, the final temperature is going to be less than the initial temperature. But I have no idea what it is. I just honestly don't know. So I just have to make a guess. Now, I could assume room temperature, and that would be fine. But I'm going to just assume something perhaps a little bit higher. Let's assume that the average temperature is 325 Kelvin. 325 Kelvin would correspond to what, about 50 degrees Celsius. So maybe we'll start at 77, maybe we'll end close to 25, and the average will be somewhere around 50, which is 325 Kelvin, and that's hopefully where we're going to end up. And if I assume that, then I would go into my tables, and Cp at the average temperature is 1.0065 kilojoules per kilogram per Kelvin, right? Now I can, at the end, check this just to see if that was a good assumption, that the average temperature was about 325. We'll see. So now that we have our value for Cp, let us continue and actually finish up the problem. So next, the first law. So back to the first law equation. So that's this one here. So let's just plug in the numbers. So we have minus 3.2 kilojoules per kilogram. And then we have Cp delta T. So we have 1.0065 kilojoules per kilogram per Kelvin, and then T2 minus T1. And like, well, you know, let's do this one a little bit differently. Let me actually use the temperature in Kelvin. So 77 degrees Celsius, we add 273, that becomes 350. I guess technically it's really 350.15, right? So 350.15, and these are actually in Kelvin. And then we have to add to it, and my arrow is in the way, so I'll just put this below. So we know the velocities. V2 is 320 meters per second squared. V1 is 50 meters per second squared. And then we divide this by 2. And we also have to throw in the conversion factor, right? For the SI units, this is 1,000. That's going to convert meters squared per second squared into kilojoules per kilogram. So we go through the math, and we solve for T2. And we end up with 297.2 Kelvin. That's great. That's right about where I wanted it to be. If 350 was the inlet temperature and 297 was the outlet, then the average temperature is, what, 324 Kelvin? And I assumed that the average was 325 Kelvin, and therefore use a CP at that average. So I'm comfortable with that. My guess was pretty good. So T average is going to be about 324 Kelvin. Close enough. All right, so I'm not going to redo this part of the problem. By the way, if you found that you just made a pretty bad estimate for the average temperature and your CP number is going to be off by considerably, well, then just go through the step one more time. You know, pick your better average temperature and get a new value of CP, and then just finish up the problem that way. Anyway, so we have T2. I'm confident with that. And now let's find the entropy change. So, you know, back to the entropy change equation. So again, now I'm going to go with this equation over here. All right, so delta S total equals, and then let's just plug in all the numbers. So we have the same CP, 1.0065 kilojoules per kilogram per Kelvin, times a natural log T2 over T1. So we definitely have to use Kelvin here. So T2 is 397.2. T1 is 77, which is 350.15 Kelvin. And then we subtract from this R. Now, I probably should have gotten the value of R when I went back into the table just a minute ago to get my average value CP. So maybe what you should do is just note, you know, we'll note A2 part B. That's going to be CP. But also, I can find from part A, I can find the value of R. So for R, for air, R is 0.287. So 0.287 kilojoules per kilogram per Kelvin. And if you forgot to get it above, then you can just do it now, which is really all that I did. So we get 0.287 kilojoules per kilogram per Kelvin, and then multiply by the natural log of the pressure ratio. So 85 over 280 kilopascals. And then we add to this Q surroundings over T surroundings. Now remember, the heat transfer to the surroundings is equal and opposite to the heat transfer to the system. So that means we're going to have to use a positive 3.2 kilojoules per kilogram. And then we divide that by the temperature of the surroundings. And again, we need to convert this into Kelvin. And now we just go through the math. And in doing so, we end up with 0.1884 kilojoules per kilogram per Kelvin. So there is another example problem that involves finding an entropy change, this time for an ideal gas. Are there any questions on this particular problem? All right. Well, the next thing I want to do then today is talk a little bit about the midterm and what you might expect to see and all of that. So again, are there any questions on the material we've covered today or homework from today? Or the example problems from today? All right, so I'm probably not going to write much more down, but I still will talk to you about the material. First of all, I just want to remind you that the syllabus tells you what sections this is going to be responsible, what you will be responsible for, section 4.3 through 7.1. But not everything in 7.1. I should note that 7.1, besides talking about the Clausius inequality, also that's where it talks to you about entropy and, you know, how one finds entropy. I'm not going to have anything dealing with entropy. If anything from section 7.1 is going to be the use of the Clausius inequality in place of comparing the Carnot cycle's thermal efficiency to the actual cycle's thermal efficiency, or the Carnot cycle's coefficient of performance to the actual cycle's coefficient of performance to determine whether a particular cycle is possible or not, right? We know that in Chapter 6, if we were given a cycle and were asked if it were impossible, possible, does it violate or satisfy the second law, et cetera, is it real? We would have done just that, right? Compare the Carnot cycle to the actual cycle. But with the Clausius inequality, we don't have to do that. So that would be the only thing from section 7.1 you'd be responsible for. And frankly, you don't even have to use it. I'm not going to say use the Clausius inequality. I may just have a problem that says, is this cycle that is described to you possible or not? Or does it satisfy or violate the second law? I mean, that's what I'm going to tell you. And I'm not going to specifically ask you for a method of solution. Anyway, section 4.3 deals with closed systems, and that's where we start getting into ideal gases, solids, and liquids. And then as we move on towards section 4.4 and 4.5, we deal with the problems. First of all, the closed system problems. I mean, at first, you were just being introduced to the whole idea of specific heats and how to utilize those. But eventually, you get into the actual closed system first law problems involving ideal gases, liquids, or solids. Frankly, the same kind of problems, well, similar to the first problem that we just did. The second one's an open system problem, obviously. But nonetheless, you'd be responsible for that. And then there was also, no, I guess that was about it. 4.4 was, I think, solids and liquids. 4.5 was ideal gases, or maybe it's reversed. But that was a Chapter 4 material, so that's a possibility. Most of the material that you'll be responsible for is from Chapter 5 and 6. Chapter 5 deals with the open systems. We looked at steady flow processes, and we looked at single stream steady flow processes, so you should certainly understand how to do those. And that would be problems involving those various flow devices: pumps, turbines, compressors, nozzles, diffusers, heat exchangers, mixing chambers, throttles. They're all described in Chapter 5. And then also at the end of Chapter 5, we dealt with uniform flow problems. Those are another type of problem that's important. Those are the charging or discharging problems, right? In other words, filling or emptying of a vessel, emptying a fire extinguisher, or filling a propane tank, something like that. So you'll be responsible for that. And then, of course, the Chapter 6 material, that's what deals with the cycles, right? That's where you learned about thermodynamic efficiency for a heat engine cycle, coefficient of performance for a refrigeration cycle. Remember, there's two types, right? We could have either a refrigerator, freezer, or air conditioner, or we could have a heat pump. So you've got slightly different equations for those. But not only did we learn about how to calculate those values, we also looked at this ideal cycle, the Carnot cycle. And this was our first real introduction to the whole idea of the second law of thermodynamics. So you could certainly see a problem like that. Some of those problems, those cycle problems, would be the ones where you have to find, like, what is the maximum work that could be produced by a cycle? What's the minimum work that could be required by a refrigeration cycle? What's the maximum or minimum amount of heat transfer? So, I mean, those are legitimate types of problems from Chapter 6 as well. So it's not just, is the cycle possible or not? You may also have a problem that involves, what would be the minimum or maximum work, heat transfer, something like that. Let me also remind you that you're allowed to bring a note card. It's going to be closed book, closed notes, except you can still use a 3x5 note card or equivalent written on both sides. And it's for equations only. No diagrams, please. No step-by-step methods of solution. No example problems written to yourself. I don't have any problem if you label your equations so you know what they apply to. But you just can't have anything on there that would, give you clues or hints as to how to solve particular types of problems using those equations. So that's what you'll be allowed. And of course, you'll have the property table handout that I brought last time. I'll bring it again on Monday. If you have your own property table handout, then you can certainly bring that. The ones I have are kind of double-sided and they're squished with 2 pages per page. But I put it on Blackboard. If you want to print it out, one side per page, and make it easier to read, then you're certainly welcome to do so. Just keep in mind, you're not allowed to write in that. You're only allowed your 3x5 card. So are there any questions? I saw a couple. Here, why don't we start here?
So, can we put that the minimum amount of power needed to heat something? Can we put those kind of equations?
Yeah, those are equations you could use, so that's not a problem. Did you have a question?
Yeah, you mentioned diagrams, but can we draw the devices, like little pictures of how they work?
Yeah, that's fine. You mean just like a little sketch, what a turbine looks like, what a nozzle looks like? Yeah, I have absolutely no problem with that. right? It's just when I think about diagrams, I'm thinking more like, I don't want you to put like a cycle diagram, that maybe like a TS diagram or a PV diagram or something like that, would show how the different processes in a cycle work. But yeah, if you want to just have a little sketch so you know what that piece of equipment looks like, sure, not a problem. Okay. Oh, by the way, I will walk around at the beginning of the test and pick up each of your cards individually, look at it, make sure there's nothing on there that's illegal, make sure the size isn't wrong. I'll bring my own 3x5 card with a pair of scissors and a big black marking pen. So if your card's too big, I will give you the scissors and let you decide how much to cut off. And if you got equations on there or something that's not appropriate, well, that's what my big black marking pen's all about. But I will walk around at the beginning and just look at those, so just be aware of that. Any more questions on content or any of the material we've covered?
So you said like, okay, 3x5 both sides, so we can do 6x10 on an 8x11 and measure.
Yeah. If you just want one side of a 6x5, like that'd be the front and the back of 3x5, something like that. But yeah, just 30 square inches. That's what would be appropriate. Let me also note that there'll be 3 problems on the test. Each one will be worth about the same. And honestly, it could cover anything in that group of sections and chapters that I've discussed earlier. Any other questions about anything?
Total of 3.
Total of 3, but some of them might be multi-part problems. But yeah, 3 problems total. And I'll provide the paper for you. If you have blank note paper that you want to bring to work out things, I have no problem with you using that too. So is that it? All right, great. So have a good weekend, everybody.